Hello, we are Team NUWC Piezo, and our project is underwater energy harvesting through piezoelectric materials. This project is sponsored by the Naval Underwater Warfare Center, otherwise known as NUWC. Our technical director from NUWC is Reed Billings. The team consists of 2 electrical engineers. My name is Matthew Duke.
Hi, my name is Sean Doherty, and we are the NUWC Piezoelectric team.
NUWC stands for the Naval Underwater Warfare Center, which is the United States Navy's leading research, development, engineering, and fleet support center for all offensive and defensive weapon systems associated with undersea warfare. This includes submarines and autonomous underwater systems. NUWC is located in Newport, Rhode Island, and employs more than 4,400 civilians and military personnel. The defense budget is over $1 billion, which demonstrates the critical role they play in the security of our nation. NUWC has a long history of developing cutting-edge technology to support the Navy's undersea warfare mission. We are honored to have them as our project sponsors and grateful for their support throughout our project. The motivation for our project comes from the need to make unmanned underwater vehicles self-sustainable. As you may already know, UUVs are mission-based systems that carry instruments and sensors to monitor, inspect, and navigate underwater environments. However, the number one limiting factor of a UUV is its power capacity, which keeps its mission limited in range and duration, often as little as 24 hours. Mission durations can be extended through the use of underwater power stations, but these have yet to be implemented commercially as they lack practical power generation sources. This is where our project comes in. Our goal was to apply the naturally occurring piezoelectric effect to generate power from sound. The piezoelectric materials generate electricity when they are subjected to mechanical stress and vibration, such as underwater sound waves. By integrating these materials into the design of a UUV, we can generate electricity to power the UUV's mission without the need for external power sources. Our anticipated best outcome of this project was to develop a piezoelectric underwater sound energy harvesting model. Piezoelectric materials generate electricity when they are subjected to mechanical stress and vibration. By utilizing this property, we aim to design a model that could harness the energy from underwater sound waves and convert it into usable power. The model we wanted to develop included piezoelectric material to generate electricity, an AC to DC rectifier to convert generated AC current into DC current, and a DC to DC converter to regulate the voltage and current, and a microcapacitor to store the generated power. Our ultimate goal was to develop a working prototype of the model to demonstrate the feasibility of generating power from underwater sound waves using piezoelectric materials. Throughout our project, we continually aim to contribute to the development of sustainable and self-sustaining UUVs. While we did not achieve our anticipated best outcome, our team feels that we were very close and that it would be easily achievable for a future project. Our project goal was to develop a piezoelectric underwater sound energy harvesting model that could convert sound energy into usable power for unmanned underwater vehicles. Although we were not able to achieve a fully functional model, we did make some significant progress. Our team successfully fabricated 6 different physical piezoelectric transducers and designed a piezoelectric energy harvesting PCB. However, due to a design error, we were not able to solder a crucial component of the circuit board, the LTC35881 chip, which integrated the full wave bridge rectifier. Despite this setback, we still managed to demonstrate our ability to design and fabricate a piezoelectric energy harvesting PCB. This experience provided us with valuable insight into the challenges of designing and implementing piezoelectric energy harvesting systems for underwater applications. Our team believes that the knowledge we have gained from this project will be useful for future research in this field. We are confident that with the additional work and attention to detail, the goal of creating a functional and efficient piezoelectric energy harvesting system for unmanned underwater vehicles will be possible for a future project.
Now let's talk about some of the accomplishments we achieved related to our research. Underwater sound energy harvesting and piezoelectric were both areas that my partner and I had never learned about, so this was a new area of expertise for us. Our first step was to learn about how sound propagates underwater to determine what areas of open water would be more suitable for a sound energy harvesting application. We discovered that sound behaves differently in water than it does in air. For example, sound waves refract, or bend, when they pass through different layers of water with different temperatures, known as thermoclines. We also learned that sound waves refract in shallow water, which can make it challenging to predict the path of sound waves. Therefore, we had to carefully select a location for our sound energy harvesting application to ensure that we would capture as much sound energy as possible. By studying sound propagation, we were able to design an effective sound energy harvesting application that would work in the underwater environment. This was a significant accomplishment for our team, and it has inspired us to continue our work in this field. Piezoelectricity was the most important part of our project. The piezoelectric effect is the ability of certain materials to generate an electrical charge in response to applied mechanical stress. This effect occurs at the molecular level, where the material's crystal structure is deformed under mechanical pressure, causing a separation of positive and negative charges, and also resulting in electric potential across the material. In our project, we needed to find the most suitable material for generating piezoelectric power underwater, and after researching various options, we found that lead zirconate titanate, or PZT, had the most favorable properties for application. PZT has a large dielectric constant, which allows it to store more electrical charge in have high mechanical factors, making it more resilient to damage from underwater forces. Additionally, PZT has been found to generate higher electrical output in response to the low resonant frequencies commonly found in underwater sound waves. We have made significant progress in designing and fabricating our custom piezoelectric transducers. We opted for a cylindrical design that suits our underwater application. Our transducer features resonant frequencies of 11 kHz, 42 kHz, and 51 kHz, which will enable us to capture a broad range of underwater noise. To ensure the reliability and durability of our transducer, we sealed it with neoprene gaskets in silicone and potted it in polyurethane. These measures protect the transducer from water ingress and provide good acoustic coupling with the surrounding water. With these accomplishments, we are confident that our transducer can efficiently harvest underwater energy and contribute to our project's success. We made some key design trade-offs that we believed were going to be better for the overall application of the prototype. Originally, we wanted to implement a resonator and a cantilever design that would sit on the bottom of the ocean and receive the widest frequency bandwidth range as possible. However, due to the specific resonant frequencies, it would be highly unlikely to generate a voltage based on such a wide range of frequencies. Therefore, we decided to narrow the frequency range by basing our project on an underwater diver propulsion vehicle, or a DVP, that features relatively small prop propulsion, giving us a better idea of what our piezo resonator frequency needs to be. Instead of piezo plates sitting on a cantilever, we featured a piezo cylinder that would have been tethered to a DVP just behind the prop. This would have given the piezo transducer a chance to absorb noise not only from the spinning prop, but also from the sound of the water rushing past the transducer. Lastly, we will quickly go over our circuit design. To begin, we utilized a schematic we found online through DigiKey and started constructing our design for the PCB using an Altium software called Circuit Maker. Our circuit is centered around an LTC3588 IC, which provides our team with everything needed to convert the harvested energy into a DC current. This conversion is achieved through a low-loss full-wave bridge rectifier and a high-efficiency buck converter. Our team plans to connect this chip to an Arduino Pro Mini, which will allow us to analyze the data that is provided by our piezo material. Overall, this circuit design provides us with a reliable and efficient way to convert the harvested energy into a usable form.
On the potential economic impact of our project, one major benefit of efficiently harvesting underwater energy is cost savings for individuals, businesses, and organizations that rely on battery-powered devices underwater. This could result in significant savings for these groups. Additionally, the successful implementation of our technology could lead to an increase in market demand for energy harvesting devices. In a world that is moving towards renewable energy sources, this demand can be huge. This could attract investors and other stockholders who are interested in the many applications that our project could have. Furthermore, our project has the potential to create jobs in areas such as maintenance, manufacturing, and installation. This could lead to a positive impact on the economy, and especially local economies on the water. Here is our system block diagram for our underwater energy harvesting project, laying out the steps to harness underwater noise, beginning with using an object that will resonate with the ambient noise, amplifying the frequency onto the piezoelectric material, which converts the sound waves into AC energy. Next, rectifying the AC energy to DC energy, and then regulating the DC energy output into our microcapacitor. Overall, it is a system designed to efficiently harvest underwater energy and store it for later use. I'd say that my biggest contribution to this project would be the fabrication of the piezoelectric transducers. First, I had to determine the best physical shape of the piezoelectric material for our project. I researched similar projects for underwater energy harvesting and found that a cylinder would be most effective. We used a piezo distributor called APC International to choose our piezo cylinders. They provided helpful information such as the resonant frequencies of each cylinder that they had available. For our project, we used cylinders 421092, 421047, and 421022, which have a radial frequency of 11 kHz, 47 kHz, and 51 kHz, respectively. Because we didn't know the exact frequency spectrum of our diver propulsion vehicle, we estimated based on sound data available from other prop-driven underwater vehicles. To fabricate the transducer, we cut out 2 end caps of galvanized steel for either side of each cylinder and used an 1/8-inch neoprene gasket material between the end caps and the piezo cylinder. Any openings between the inside and outside of the cylinder were sealed using silicone, and we coated the outside of the transducer with a 2-part clear, colorless polyurethane elastomer to make it waterproof. And now I'll hand it back to Sean.
My technical contributions included piezoelectric research, then most importantly the design of our team's PCB. For our design, we wanted a small device which could be fit beneath our transducer design in a waterproof bottom cap. I was able to find an IC that was directly made for energy harvesting, specifically using piezoelectric material. This included a rectifier with a high-efficiency buck converter to form an energy harvesting solution optimized for high-output impedance energy sources. In our case, this was the piezoelectric material. Also, finding ideal capacitor values for our circuit based off our estimations of the output voltage from the piezo material was another contribution made by me. Lastly, I wanted to be able to read our data that was being produced from the piezoelectric material after it went through our circuit. I did this by implementing an Arduino Pro Mini where we'd be able to read the analog values of the output voltages, as well as a Bluetooth module, so when the device is submerged underwater, there is an ability to read the data from the Arduino using the Bluetooth in real time. We would like to extend a special thanks to Dr. Sunak for giving us the amazing opportunity to work with NUWC and gain invaluable real-world experience in our field. Your support and guidance have been instrumental to our success this far, and we are truly grateful for your commitment to our project. Your encouragement to explore our passions and ideas have been an inspiration to us all, and we look forward to continuing our work under your guidance in the coming semester. Thank you so much. Before we conclude, we would like to extend special thanks to Mike Smith, Brendan Smirback, and Jack Murphy for all their invaluable help and guidance throughout the Capstone program. Their expertise in risk management and project progression has been crucial in ensuring that our project stays on track and meets all of our goals. Thank you, Mike, Brendan, and Jack, for your dedication and commitment to our success.